Okay, so in this video, what we're going to do is we're going to look at the rotational kinematics equations, and they're very simple because it's just a matter of taking the linear kinematics equations and substituting in the rotational variables. Okay, so one thing to remember is that we have x, which becomes theta. We have v, which becomes omega, right? So the kind of the regular letters are the linear aspects. The Greek letters are the rotational aspect, and so acceleration, or a, becomes alpha. So here are the equations. You got v equals v0 plus at. And it's also a good way to review the equations. Remember, this is the vt graph equation, right? And so it's a line. And then we have delta x equals VOT plus 1/2 AT squared. This is the position time graph equation. Then you have V squared equals VO squared plus 2A delta x, which is important because this equation has no time. And remember, there's 5 variables, and in each equation it's going to have 4 of the 5. And the same thing holds true with the rotational equations. And then we have the one that's often not given to us on formula sheets. You got 1/2 equals, delta x equals 1/2 times v plus v0 delta t. This is just another way to write the position equation. The thing about this one is that there's no acceleration. So if we're going to write the rotational equivalents, all we have to do is replace all the standard letters with the Greek letters. Okay, so let's go for it. So first equation, omega equals omega 0 plus alpha t. So all I did was I flipped out, right? V became omega, A became alpha. And one thing to note is that time doesn't change. Again, time doesn't care about direction, or if it's traveling linearly, or if it's spinning, rotating. It just cares that you started a stopwatch and you stopped the stopwatch. Okay, the next equation, delta theta equals omega 0 plus 1/2 alpha t squared. Again, we're just flipping out those variables. And you're going to use the equations in the same exact way. Next equation, omega squared equals omega 0 squared plus 2a to alpha delta theta, right? We're doing the rotational equivalents. And then finally, our last equation, delta theta equals 1/2 times omega plus omega 0 delta t. Again, 4 of the 5 variables exist or are present. And again, the one variable that is in all of them is our initial velocity, our initial angular velocity. And you can see here in the linear equations, the one that is in all the equations is initial velocity. Okay, so remember that, again, time, this is important. Time doesn't care about the direction, just like we talked about. It doesn't care if it's traveling horizontally or traveling vertically. It just cares that you've started a stopwatch and you stopped the stopwatch. Okay, so one thing to remember with these equations, especially at the AP Physics 1 level, is that the angular acceleration is constant. Right, we called these equations, right, cake, constant acceleration kinematics equations. Well, you can kind of talk about the other ones as like cake, right, constant angular acceleration kinematics equations, right? So the double A is angular acceleration. Okay, so let's look at some examples. And as I mentioned, we're just going to use the same, use them the same way that we did the linear equations, okay? And so here's an example. A point on a rotating tire is completing 20 RPMs. A tire begins to uniformly slow at a rate of 0.2 radians per second squared. How long will it take for the tire to come to a complete stop? So the first thing is we need to take that 20 revolutions per minute and change that to radians per second. So remember, 20 revolutions, remember, 1 revolution is 2 pi radians. So 2 pi is 1 revolution. and there are 60 seconds in 1 minute. So we're just really going to multiply 20 times. Sorry, I have this backwards. This should be flipped. So 1 minute is 60 seconds. So we're going to multiply 20 by 2 pi, which is 40 pi, which is about 120, and divide it by 60 seconds. And so our initial angular velocity will be 2.09 radians per second. Okay, we don't have to do anything to the angular acceleration except put a negative sign in front of it, because it tells us that it is slowing. And so since we're looking for a time, we're going to do omega equals omega 0 plus alpha t. Our final angular velocity will be 0 because we're slowing to a stop. And so we're just going to solve this for t. So t equals negative omega 0 over alpha. So negative 2.09 divided by negative 0.2, and it'll give us a time of 10.5 seconds. Sorry, my S looks like a 5 also. Okay. Negative divided by negative, again, would be a positive. Remember, time is always going to be positive. So it's going to take this tire 10.5 seconds to come to a stop. Okay, so here's the next one. A centrifuge in a medical laboratory is rotating at an angular speed of 3,600 revolutions per minute. When it's switched off, it rotates 50 times before coming to rest. Find the constant angular acceleration of the centrifuge. So again, first thing we need to do is to convert revolutions per minute. Same conversion as above, right? So 2 pi radians is 1 revolution. 1 minute is 60 seconds. And so that's going to give us 377 radians per second. Again, remember, you don't have to put your calculator in radians because we treat it as like meters. And then we also have to convert that it does 50 revolutions. And so all we're going to do here is say 2 pi radians is 1 revolution. And so this is going to end up being 314 radians. Okay, and so we're going to look for the angular acceleration. We know it should be negative because it talks about coming to rest. So it's going to be our final velocity. And so we're going to use the equation with no time because it doesn't give us a time and it doesn't ask for it. Okay, where omega squared is going to be 0. And so alpha is just going to be negative omega 0 squared over 2 delta theta. This is going to be negative times 377 squared over 2 times 314. Again, don't forget to square the 377, the initial angular velocity. And so that's going to be negative 266 radians per second squared will be our angular acceleration. All right, so now when an object is moving in linear motion, so when it's just going in a straight line, and sometimes we'll call this translational motion, about an axis, we can use properties of each to analyze the situation. Okay, recall that when objects are in circular motion, they experience a centripetal acceleration. But there is going to be a difference as to what, which acceleration are we really talking about. And remember, the equation is going to be a sub c equals v squared over r. You got to go way back to when we talked about gravitation for that one. And then, but we can also use the equation v equals r omega to develop a new equation. And so what we're going to say is a sub c equals v squared over r. But what we're going to do is we're going to put r times omega for v squared, and you're going to get an equation of omega squared r. So that's just a new way to write the centripetal acceleration equation. And so we're going to use that in this example here. It says a beetle is placed at a point 1/3 as far as the ladybug from an axis of rotation. A, how does its centripetal acceleration compare to that of the ladybugs, and explain. And then how does the beetle's linear velocity compare to the ladybug's linear velocity and explain. And so let's use our factors of 1, right? And so we're going to say a sub c is omega squared r. Now, the thing is, they're both on a rotating disk, so they're going to travel at the same rotational velocity. And so what we're going to do is we're going to call that 1, right? 1 squared. And we know that the beetle or the bug, right? The beetle is placed 1/3 away from where the so this is 1/3 the distance of the ladybug, right? We'll call that LB for ladybug, okay? And so their centripetal acceleration will be 1/3, okay? And why is that? It's because they're 1/3 of the way, right? They're 1/3 of the radius away from the center of rotation. Okay. Now, how does their linear velocity compare? Well, we do the same thing, right? And so we're saying that the ladybug is the original, but again, omega is going to be the same, but you could see that the velocity will also be 1/3 of the ladybug's, right? And so the velocity of the beetle will be 1/3 of the velocity of the ladybug. And here, the acceleration of the beetle will be 1/3 of the acceleration of the ladybug. Okay, so this really ends the kind of the kinematics portion of this unit in the rotational motion. And what we're going to do is now we're going to start comparing and looking at how do we equate force to rotation? Okay,